Hello, everybody, and welcome to Handmade Hero, show where we code a complete game live on stream. We are basically going to, switch. We're going to switch gears a little bit today because I don't know if you saw what I posted on Twitter, but basically I realized that what we were doing was dumb, and I should have thought of it beforehand, but I didn't. Anyway, if you take a look at where we are, we were trying to do some work on optimizing how we were doing ray marching. I guess it's just ray tracing. But if you take a look at how we were doing it, one of the things you can see is that we were in our lighting profiling. When we were actually doing our grid raycast, we were trying to see if we could just march through the grid in a computational way. So like down here, we've got code that has the old way where we look into a table and then a new way where we just compute what we're doing. And I wanted to look at what the timing difference would be between these two. And it turns out that the answer is it's quite bad, right? So even though we did a sort of pseudo optimize, and we didn't really optimize it particularly heavily, but we did, it's not much, right? It's 10 instructions or something. It's not huge. It turns out that this is just way too much, probably because this is very predictable and straightforward for the processor, and this is actually a bunch of computations and then a thing where you have to actually depend on those computations. So this can just be fired off immediately, and this probably created some kind of dependency chain or something. I don't know. But it was quite a bit worse. Now, that doesn't actually mean that it is worse. It could be that if we worked on this, we could get it down. But what I realized is that may just be a waste of time, because if you take a look at what's going on in here, I realized that there's no reason we can't just use the walk table and still use larger grid sizes. So originally the problem, and maybe I'll sketch this out on the blackboard because this was just something that I happened to randomly think of in the middle of the week while I was doing something totally unrelated to Handmade Hero. It just pops in your brain. I think I just have background processes that are spinning on code, and they just complete randomly and say, oh, hey, by the way, this was dumb what you did. And I'm like, oh, yeah, it was. So anyway, on day 617 here, what table driven raycast. So basically what was happening before is all right, so we know that the way that this thing works, and I guess, I can use the fancy little grid thing. There we go. Is we have a lighting voxel, and we know that we're going to cast from the center of these voxel points to create our probe values, right? So we're picking one of these, right? And we're in this voxel, and we're going to send out all these rays, right? So for any given ray, what we needed to do is go, okay, we need to figure out how this ray marches along, and we would just say, look, what geometry is in each part of this voxel as we go, and that's the whole thing. And since we know that we're always starting from the center, we know that we can just, for each ray direction that we want to cast from our table, we just have the series of grid squares it goes through, right? So that's really nice and convenient, and it just allows us to table drive the search. Problem is, it depends on the lighting voxel, right, equaling the spatial voxel. So, or the spatial hierarchy that we use for determining what occluders we test the ray against for intersection. So previously, we had to have the lighting voxel and the spatial voxel be coincident, meaning they had to have exactly the same size. And the reason for that was because you always had to make sure you were starting in somewhere that coincides with the table. So if the table was built for some other grid, right? So, if we had just done oh, well, here's this other grid we were doing or something, right? And the walk was supposed to be along that, so it would do here and then here or whatever, right? because then you could be casting from all sorts of different offsets relative to this grid, the table would never line up with the cast anymore. So I was like, oh, well, what if we just dynamically compute which grid squares to go through? Then we could use any size, and I really want to be able to use bigger sizes because I think that would speed us up. Right now, we don't get enough leverage per grid square. But what I realized is that's not necessary. All you really need to do is know that there's a correspondence between these two things. So sure, we can always do the grid walk along this thing if we want to, but we can then also just use that as a mapping into our spatial occupancy table. So for example, suppose we said, look, what we're going to do is we're going to use like 3 or 4 or 2 or something. We're going to group these squares together, right? Like so. And so we'll basically have a low resolution grid and a high resolution grid, right? And then we know that there's 2 ways we could now approach this problem, and I don't know which one of them will work. Maybe neither of them, in which case, we're still back to square one. But we can do one of 2 things. One thing we can do is we can just loop through each grid square, and we only need to actually do testing when we detect that we've actually moved into a larger square. So we can just keep whatever our coordinates were and go from there. Or we can do just something which multiplies out our table more. So we can just say, look, we know we're always aligned. We're just aligned in one of 4 or 8 ways, right? And the problem is the table gets bigger, right? But the runtime cost wouldn't. If that makes sense. So in that particular case, it's like, well, all right, it's really hard to say, will that be more efficient than what we were trying to do? Because it's in that sort of cloudy area of like, what does the processor want to do? And I don't actually know, but it seems worth doing to try to get the table to be, to see if we can just make a table that's similar in size to our existing table, but that actually just lets us walk directly without too much of a problem, right? So that's the thing that I would like to take a look at. Now, one of the things is we could just expand the table directly. Now, remember, the problem here is that this is actually 3-dimensional, so it's not going to be 4, right? It's actually going to be 8 if we group these up, right? It's going to be 8 of these cells. So if we just did this directly, our table would be like 8 times the size that it was before, which is quite it's quite a increase, right? And I don't know that there's much of a way you can really compress these. It's a good question. So like, for example, if you're always going to start in one of these 8 quadrants, or 8 octants, I don't actually know whether you need to store completely different walk tables for all of those. Like, it could be that they're mostly the same set of walk tables, or that there's a way you can adjust the values fairly trivially to make that work. I don't know. So there's a lot of things there that I don't know. And another thing that's worth noting there is there's the possibility that it could be compressed in some way. For example, let's suppose that you have two different rays and both rays traverse the exact same set of cells. And the larger you make the cells, probably the more likely that's going to be as well, right? Because the larger the cells are, the less variation there's going to be between two different rays, because there's a much wider aperture that could catch, you know? So just to give a simple example, suppose we took a grid like this and we said, well, okay, we're going to take these two rays. If we were talking about a grid that was exactly the resolution of this, then these are not the same walk table set, because one of them diverges and comes down here. Otherwise, they were the same. Like this 4 was the same, but then these 3 are different, right? But what you'll notice is that if I was to then say, well, what if we had the grid squares be this large? Then all of a sudden, if they're 2 by 2, this is maybe the same, right? So it's possible that that could be the case, but I don't really know, right? Like I don't know to what extent that would really be true. And the reason I say that is because if you think about what happens if you move this one down, then they are different, right? So really hard to say, and I'm not sure. It's a really tough call. So I guess what I would say first is maybe let's see what happens if we just try, right? And we'll see where we get. And based on what I see, we'll determine what our next steps are going to be. I really just don't know exactly what the right solution here is. But so the other way to do it too was just to say, look, let's just still march on the high res grid and then just correspond back to the low res grid. And that method's super simple, right? All we would do there is just, instead of having an absolute delta, we would have like a delta per channel. So we'd actually track the XYZ in, an actual, an expanded. So, maybe we'd just do like 888 packed into a register, and then we'd just convert that into a high res grid lookup by a few bit shuffles, right? And the problem with that, because that's by far the easiest and it doesn't change the table size stays the same, and would probably be quite fast. The problem that we have with that is that I have no idea how we would actually step it, because each step in the high-res grid doesn't necessarily translate into a step in the low-res grid. So you would have to have a loop, like a separate loop that happens at the end of the main loop, to keep stepping till you got to a new one. And that just sounds dicey. That sounds real bad, right? It could, in theory, be done with like conditional moves, so that you don't have any branches and no loops. And that's because you can't take more than 3 grid steps without getting to a new one, right? There's no plausible way you could hit 3 grid cells and not have the next step take you out of the grid, I don't think. And maybe it's 4. I'd have to think about the fully 3D case, but it's something like this. So you could do like 4 conditional moves, and therefore not have a loop. But I just don't know. It sounds bad, right? And we can try it, but it sounds bad. So again, pretty sure that there's probably there's something here we can use that's better than computing it on the fly, like we were. Which, even though it was fairly concise, it seemed a little too expensive. I don't know what we can do exactly here, but I think it's just worth looking at this as an alternate method of trying to get that grid size to be larger. So just to be clear, what I mean by that, if we take a look at our voxel, so I guess it's in the renderer that specifies how big it is, right? So you can see here that we've got a 24 by 16 by 16 voxel. And so you could imagine doing like a 6 by 4 by 4 or a 12 by 8 by 8, right? And again, we'd leave the lighting at this resolution, but we're just talking about the spatial occupancy grid. And the spatial occupancy grid would be smaller. So as a simple first test, what I'd like to do is I'm just going to nerf this code here. So we're not going to run the branch of this code that does that does the the computed step version. And I'm going to go ahead and do a run of the profiler. And if we take a look at the cost for our current scheme, it's 4.5-ish. It's been that way for this scheme. And what you can see is here's our box count distribution, and you can see that like we just have a lot of trouble getting high box counts. We want more of these because we're doing like way too much work right now on the grid iteration, I think, and not enough work in the actual box loop. It's especially true because we have fairly sparse areas right now, which, may not be true always, so I don't want to like try to push this number down artificially, but you can see here we hardly ever get like large. We'd like to be able to do like at least 8 per cell, because otherwise we're just spending a crap ton of time on loop overhead, right? And we almost never get there, right? We almost never get there. Like the number of times we have stuff in the upper size of things is really low, and when we do, we're usually wasting like some of our lanes. We really want to push this up. We want to see a lot of 7s, maybe even a lot of like 11s and such, or 12s. We just want to be pushing up towards the like higher capacity for the test throughput inside a grid square. So I just want to do a little bit of testing on this first, just kind of like push it around a little bit. And so if we take a look at when we actually do the grid initialization, that part where we compute the spatial grid, I want to see to what extent I can muck with it. Now, the problem is I'm not sure how much of this is really... You can see here we do some testing, and we do stuff like looking at the atlas cell count, and if the atlas cell count differs, then we do stuff like making these grids. And so that part's, I think, probably a bit of a problem because, I guess it's not that big of a problem because I can just make these calls separately, I suppose. And that would probably be fine. So in here you can see where we do the spatial cell count. You can see it taking the atlas cell count and just adding a gutter, right? So if we wanted to, what we could do is just drop this, right? We could just drop this down and still do the part where we actually do the spatial grid. That probably would all work. So what I'll do is I'll do that inside HH Lightprof here, and we'll just see what happens, just to see if I can, sort of poke it a little bit and get a sense for it. So when we load the solution here, what I'm going to do effectively is just overwrite it, right? And again, this is just because we're in the test code, so we don't, we're not running the normal init code because we're not actually running inside the game when we're doing the test. So in here where we do like vox cell dim, well, the cell dim can still be the same, so that's not really a big deal. we do need to know what the fundamental unit is, but I think we kind of know what the fundamental unit is always, because it's always the same. So I can, again, hard code that just for this test. You can see that it's like 1.4 here, right? So what I could do is I could just say, look, the fundamental unit is 1.4 for all of our testing. So we're just going to hard code that in while we're just doing this hack to see what's up. And so then all I really need to do is take this spatial cell count here. And when I do this computation, this atlas cell count, I'm just going to divide it by 2, right? So we're just going to decimate it by 2. And then we're going to set all the rest of the stuff up. This can stay the same. This can stay the same. So it's just this. It's just this spatial grid where we do make voxel grid. That's the only thing, right? Okay. So when we look at this, we need to know what the atlas cell count actually is. And I think the only real way for us to do that here is to look inside the solution. And so if you take a look at the lighting solution, it has the atlas. Well, I mean, you can see here, it's got the atlas grid in it. So I think we would just do inside that, where's our voxel grid? There it is. So inside the voxel grid, you can see it's got that cell dim there. So we can just look that up because we did save it to the drive. All right. Oh wait, it's actually cell count. Sorry. I don't know what's going on there. All right. So this would produce a different spatial alignment for this, right? It would produce a different sort of placement for it. And I think the other thing that we're going to run into here is when we make this voxel grid, I don't know how it figures out where the corner is, right? Because that's going to be a little bit weird. So the total bounds thing here, I guess the answer is that gets set periodically, probably, I would think. So it's probably in here, right? Where we're going to call set min corner. And so we need to take a look at the set min corner call and just see what's going on here. And so you can see the way that we were doing this, right? So we know where the atlas min corner is, and that's fixed in position. And then when we need to set our spatial min corner, we need that to be aligned. So we're basically saying, look, it's here. And what you can see is we use this thing called atlas to spatial grid offset. And I don't necessarily know why we chose to phrase it this way, meaning multiplied by the cell dim, instead of just having that be the case, because cell dim size doesn't change. But either way, it's okay. If we take a look at where that's actually computed, which would presumably be in here. Where's the offset? Yeah. So if we take a look at this, we can adjust this value as well. So now, like, effectively what's happening here is, since when you look at, like, this vox cell dim value here, the vox cell dim value always comes from the atlas. It never comes from the spatial grid. So in terms of setting up where the spatial grid is, we can just say, look, it's going to be 2 now because we are twice as large. And that's just one of the reasons why I was saying, like, I don't know that we really want this to be based on the vox cell dim. I mean, I would pretty much say to do probably just make atlas to spatial grid a vector, not an index. So I don't know. I mean, maybe we don't want to do that. I'm not sure. If we look at where that's actually getting used, I guess the problem we have is that we're trying to do like this sort of offsetting where we say, like, here's the voxel we're in, and then we want to just add something to it. I think we need that to probably be a more complex mapping, right? Because this is not going to be correct anymore. So you can see why I think like this used to be fairly straightforward because we knew that they were aligned, but it's going to need a little bit more. Trying to think of what to call it. It's going to need a little bit more flexibility. So when we're doing this and we say, hey, we need to get a grid index out of this thing for the walk, this is no longer, it doesn't make sense anymore, right? For this to just be a flat offset because it's not ever going to be correctly indexed. The spatial grid is going to have a like a scale value as well as an offset, right? Is the way to think of it. And so in addition to offsetting it by 1, like you can see this wants to be, 1 potentially, but in here we could say, all right, we add these together and then we divide by 2, right? That would give you the correct index. So you can see we probably want that to be systemic. Like we want that to be something that we know where it's happening, right? But otherwise, that's really all we would need to do. And at this point, I don't actually know if that takes care of everything, but it probably doesn't yet. So you can see here, like we got some weird results there, but that's basically what we want to do. So box count 0, that doesn't really make any sense. What we're seeing there, so we have to go figure out what the heck is going on there, right? But that's basically what we want to do. So when we make, when we made this atlas here, voxel dim looks correct. Spatial cell count is this divided by 2 plus 2 times. Oh, well, that's actually not correct though either, right? So really, this should just be v3s 222. Like so. I mean, again, we kind of have to make this a little bit more systemic. But so let's take a look at why this is happening first and try to start to clean that up. Because I think this should be mostly correct now. And we just have to go figure out, like they probably missed 1 or 2 things in there. Because this is a pretty weird thing we're doing here. So let's switch to debug build. Oops, that's not the code I wanted to run. Okay. So what I want to do now is I just want to start taking a look at what's actually happening in here. So when we do our lighting init, I just want to look and see what's happening. Do we not call that function? In the light prof, we might not. Let me get us into this location first. Okay, so let's just take a look at what these values actually are. So here's solution, atlas grid, solution, spatial grid. Here's the cell counts. And those look about right. So these values presumably won't get set till later. So we'll see. I'm not sure, because yeah, you need set min corner. Oh, So you know what? Probably we have to force the set min corner to get called though, right? Like, now that I think about it, since we're probably just calling yeah, we are. So the problem that we're going to have here is this is not going to be aligned anymore. So that makes sense. So if you take a look at the way this was working is, you have to call update lighting, get these things aligned. And since we just save it out directly, we were just loading it in from the actual game scenario and running it. But that means we never actually do this call, right? So we need to, if we're going to reset this thing, we need to actually have some way of setting up the spatial min corner. The spatial min corner in this case, we would get the atlas min corner, which we can get pretty easily because we haven't changed it. And then we need to just set the rest of this stuff up. So you can see here, like, we need to figure out how this would actually be aligned. We know what the voxel dim is. We could have gotten this out of the atlas, so I don't know why I bothered with this. Like, we could have just done this, right? So yeah, I don't know why we didn't do that, because I'm pretty sure these are aligned to fundamental units anyway. So anyway, yeah, like if you take a look at how this works, when we go ahead and get the minimum corner here, we then just need to adjust by however much the offset is that we wanted to do here. And I mean, I'm pretty sure that's just correct. All right, so let's take a look. And let me just see what we get now for box distributions. I don't know why that's so apparently still wrong. So apparently I'm not correct. I figured that would be the main problem because that just doesn't set any dimensions on it, right? So let's take a look at the spatial grid here and see what it thinks. So here's the new dimensions for the spatial grid that you can see here. Oh, yep, I know what the other problem is. So the other problem we're going to have here is that this vox dim is not correct. So if this is too wide, right, it's got to be, right, it's got to be 2 times the size for the dimension, because it's going to be twice as long. Each individual cell will be twice as long, right? So yeah, so in here we need to change this up. So this is going to be 2.0, right? This is actually just going to be 1 at that point. And this, yeah, I don't really know how we want to phrase this, but this is going to be more like that, right? So it's just going to be 1 cell around the outside, and that's always going to be true. So we wouldn't really need to multiply that. That should be fine. And the index offset, again, like, I don't really know, like, exactly how we want to phrase that, but you can see here the way that is phrased. If I jump up to, sorry, I just got to type that in here. When we do the flat index from, and we do this offsetting here, again, that part is, yeah, it's not really clear what you want to do. So I think this 1, 1, 1 would still, this would actually still be fine, because we could have just done this, left it the way it was, and we just put that in. So I don't know. I'm really not sure how we want that to be phrased, but we're going to have to look at that separately anyway. All right, so now if we take a look at what the box distribution is, maybe we can see a little bit more clearly what's going on here. So again, not really sure I understand what I'm looking at. I think we may still have just a problem in here with how we've set this up, because just looking at the total box numbers, is that, oh, well, you know what? No, that could be correct, because one of the things that you'll notice is, like, if we take a look back at the original box counts, you can see how many input boxes there were. Look at how many splits there were. Like, there's only 1,251 boxes, but this is how many actual splits we ended up with, right? So there's way more. This would, if this is correct, which it may well not be, it's much, much lower, right? Okay. Sorry, I just glanced at chat. Everyone on the Twitch chat who's here regularly understands what I'm talking about, right? I would assume that like it would only be people who are just dropping in for the first time who don't know, because we've gone over every last little bit of this on the stream. So people who've been watching, they know what I'm talking about. So anyway, looks fine, right? And I think I was right about this, because if you just look at how many fewer total boxes there are, now that could just be a premature victory lap, because it could be the case that actually this is just buggy. And, you know, the binning is just going wrong or something, right? But if you take a look at that, even just that doubling in size produces just such a much better arrangement here. We are mostly up in the higher numbers. There's very little down here. And the number of 0 cells dropped dramatically. It dropped by a factor of 7 because now there's like larger empty space areas there. And so that's really important too, because we want to traverse empty space as quickly as possible. We don't want to spend a lot of time looking at empty space and going, is there anything here? Is there anything here? Right? That's not doing anything for us. We want to try and get to the places where we might have intersections as quickly as possible. So we can still run, like we can look at this and say, oh yeah, okay, so you know we can still run here, and I don't, to be honest, I'm not sure how we're doing the clamping. This should have crashed, I want to say. Well, no, because the initial grid index wouldn't. So I guess it won't crash. But we're not actually doing accurate testing here, right? We're doing who knows what, right? So I just wanted to see what the difference was in runs, and it looks like it actually doesn't affect the runtime very much at all. It's basically the same, which is a little surprising, honestly. So I'm not sure why that wouldn't have improved our performance, but it's a little bit hard to say because we're not actually doing anything correctly now. The walk table is, you know, completely wrong for what we're asking for. So it's just trying to think of how to say this. So it's although the initial grid index is going to be correct, the way that this was structured, the actual walk would have been wrong, right? Okay. So I do know that the breaking down of the cells into too small things does create problems for me, but I don't actually want to do that fix yet. I want to leave that out. And the reason for that is I want to make sure that in this code path here, where we're doing this sort of initial grid index stuff, what I want to do is change to passing something that's actually whole indices. So if we take a look at the places where flat index from is called, so in here where we've got flat index from, I'm just going to go ahead and say, look, let's nerf that call real quick and just see where it's called. So you can see here we have flat index from getting called often, right? And when you produce the flat index from, it's basically just the way of saying, look, which of these grid nodes are you going to access. Now, there's a couple ways I can do this, but I'm going to need like this other thing. I'm going to need voxel, I don't know what we want to call this, sparse index or something. And I'm going to need like a way of saying, look, we want to pack the values into one thing so we can still do like addition and subtraction and crap on it, but we're going to need some way of doing that cleanly. And to be completely honest, I'm not 100% sure exactly how I would want to do this, but I think, if I'm not mistaken, we should, because we don't ever overflow or underflow on the stepping, these should be things that will, where you can still use a single value to update it, but the actual indices for X, Y, and Z are all kept separate, right? So if you imagine something like this, put this in the same place as the flat index. So if we put this in here, and we want to do the same assertion, presumably just to make sure that it always actually is inside, and then we do something like this, you can see, like, I don't actually want to do this anymore because I want to keep these separate. So instead of getting the cell count, what I'm actually going to do is I'm just going to OR these together. Right? So what I want to do is I want to have my X, my Y, and my Z, and I want these to be just combined into one value. Now, if I just ordered them directly together, obviously this wouldn't work because I would basically smush them all on top of each other, so we'd be no way to get them back out again. So what I want to do here is just spread them out. And since I know that I'm not going to have voxels that are particularly big in this case, what I'll probably do is say, look, let's just give each one 10 bits. So, you know, something like this. And, you know, I mean, I guess if you really wanted to, you could say, let's give each one 11 bits. And since we know Z is less, you could make that particular one not have 11, right? So you have like X and Y have 11 or something. You can do all kinds of stuff, but it doesn't matter at the moment because we know that 10 bits is way more than we're ever going to have because we can't afford to do something budget-wise that's that dense. Like right now we're talking about 4 or 5 bits total for the index, so that's twice as many bits. We're never going to get there. It would be great if we could, but we're never going to. So anyway, if we take a look at the sparse index here, then what we can do is we can use the sparse index to do various operations, right? So what we want to do is now have a way to use the flat index to look up into the... We want to be able to take a sparse index, and we want to be able to look up, using the sparse index, into a particular voxel grid. And so effectively what we're doing there is producing a flat index. You know, we're doing this operation, right? And so we want something that works basically like this, where we can produce a flat index from, and we more or less just want the same exact call, just flat index from, and instead it's going to take a voxel sparse index here, right? And then in addition to that, we're going to want some way, right, of, like, we probably want this sort of hard-coded almost, because when we're doing this indexing, we want to have some way of reducing the order. So like in the same way that we were doing a divide by 2. So what we want to do here is say, look, we're going to do a flat index from our sparse index, but we know that these indices are going to be kind of in the wrong dimensionality or something, right? So there's, again, a couple of ways we can do this. And this is how we would do, again, I don't know which one we want to do, but this is how we would do the version where we step in the high-res voxel, but still use the low-res voxel. So this would allow us to step in X, Y, and Z using an offset, and then we would just unpack these values and shift them by an extra bit to divide them by 2 and then do a lookup. And that would be very, simple for us to do and pretty efficient. So the only problem that I have is I don't know if I want to do that. I don't know if what I'd rather do is just table drive the thing by generating 8 different tables depending on which one of the grid squares you're in. So if you're in, which one of the octants you're in a larger grid cell. And I don't have any, I just don't know. So here's a thought. You know what? Forget this. Because here's my argument. Here's the argument I'm going to make. I think I can safely go with build the additional tables. Here's why. Sure, there's 8 different ways you can be inside a grid cell, so the table gets expanded by a factor of 8. That's a lot, right? But you're going to walk like half as far, possibly 2 root 2 as far, depending on how the ray goes. So the table also contracts by half. So it's really only a factor of 4 expansion, which is still bad. But not as bad. So I'm going to say let's go with that first. So let's just do that first. So in order to do that, again, so this initial grid index now has to be something that we preserve and pass down, because this flat index is not going to work. So what we're going to have to pass down here, rather than any of this stuff, we're going to have to take this atlas index and send it down directly. So I'm just going to start by trying to do that. And what I'll do is say, all right, let's look at atlas index here. Where were we passing the flat index? Here you can see us passing it in. So I'm going to say it takes the whole thing, right? Like so. If I go up to full cast, you can see it passing it here. So I'm just going to say, look, this is the atlas index again, right here. And then when that gets passed in, you can see here it's starting to get used, and it's doing a lookup here into the spatial grid to see whether or not it's inside something. Okay. So if we now go and say, all right, we need to figure out where we actually are in our grid. So for the atlas index, we know that this would give us the actual grid square that we're in. We would divide this by 2 and then add our 1 offset, right? So this is actually correct. And then we would look that up in the nodes, right? That's a correct usage of that. But this isn't. And the reason this isn't is because in grid raycast, we expect this thing to actually have different information. So what we would need here is when we look up the walk table offset, so this bit here, we would need to use the walk table offset in a different walk table, right? So this, where we do light sampling walk table, this needs to actually have like a dimensionality to it. And so what we're going to have to do is have like a octant index, right, that we look up here. And so the initial grid index, which would come in and is, I guess to be fair, it is the correct one. Like, we did actually get it. So this isn't, fake. And I guess I can do this in 16. So it's not wrong, but it just is incomplete. So in addition, we need the octant index, and really that's even smaller. That can not be very much of anything, really. So in here, where this actually looks it up, we would need a bigger table. And then in here, in addition to the grid index, we would need the octant index too. And so when we do this actual initial grid index here, what we need to do for the octant index is we need the remainder, right? So we're going to have to do like a half index. We're going to have to say like half atlas index. Like so, and then we're going to have to actually do the remainder. So the remainder from that is the atlas index minus the half atlas index times 2, right? So this is how many we had left over. Now I don't know how we want to encode this octant index, but presumably the easiest way would just be to say, look, we're going to take the remaining x, which is either 0 or 1. We're going to add it to 2 times, you know, or we can even do this. So we know the remainder is always 0 or 1. We divide it by 2, you can't have any other remainder, right? And it was a positive value. So once we have this remainder, we're just going to say, okay, x goes in that bit. Next bit up is y. Next bit up is z, right? So we can pretty easily, decode those values, and we can make this an actual function so that it's, not so mysterious. And so here, if we say like somebody computed a remainder somehow, right? And we want an octant index from a remainder, well, here it is. And again, that's just so we don't have to like have that, the way we decoded that. We don't want to strew that throughout the code, because what if we change it, or who knows what. Just also for clarity. Okay, so I think that's really all we needed there. And so now the problem we have is this, and we don't actually have these tables that we would actually need. So here's the lighting solution. And what you can see here on this light sampling walk table, we kind of have a problem, which is that if we change this, we will break the loading because we just flat saved it. So what we may want to do is something like this, where we just push this down here, right? Because this stuff doesn't have to, be changed, or it doesn't really affect us, right? So we'll just put it to do in here. But that's basically what's going on. So in the light sampling walk table, and in fact, I guess I can just leave this at the very end. I mean, whatever. So we can now generate this in a way that we say, look, we know there are 8 octants, so we can generate each individual octant for this thing, and off we go. But our problem now is, well, we're going to have to actually compute that somehow. And so when we do compute walk table, we're going to have to take into account all of that stuff, right? So if this is 8 long, and I guess another way to look at it would do this. If we go to compute walk table, like so, let me say this thing returns now like an array of pointers instead of whatever. And I don't know, this is getting kind of annoying now, so I feel like I want to stop doing that. Like I would rather this thing just did what it's going to do. So, excuse me. So what I'd rather do here is say, okay, the walk table entry maybe is a thing that, is taken as a dest, so it doesn't, you know, write out that way. Oops. Where did my code go? Well, the compiler will take me there in a moment. There we go. So anyway, if we, just say, hey, go ahead and build that. I also don't know compute walk table fast. Let's get rid of this because we're not going to be using this anymore. All right. All right, so then I think we're good. And now we just have to make sure that we don't want to call compute walk table fast anymore. It's not a thing we use. It was just some test code. And we do want to pass that in. Wish I had some more T, but I don't. So I think that's the end of it. Yeah. Okay. And so now what we need is we need compute walk table to actually generate different versions of this table, right? And what we want to do here is take a look at that max cost per array. So max cost per array, I mean, I guess we don't have to care at the moment. I'll put a to-do on it, but in the past, we were sending down a much higher value than we should have. So we were sending down 16. And if we have the size of the dimension of the grid, that should shrink to 8, right? Because we're no longer going to need to visit as many grid cells to get the same distance. So I think that's probably pretty safe to reduce. So in here, I would also say, okay, where we were setting that to 16 before, we can probably safely set that down to 8. And for now, I'll also, inside our sort of temporary code inside HHLightProf, I'll do that as well, right? So all that should be fine. And we can, drop the number of grid squares that you visit down. Maybe I'll do it this way because I want to just be clear that that's temporary code, because if we build our test data, that would get properly slipstreamed in. So I think that's all we need there. And then inside compute walk table, I just need some way of having compute walk table actually build the different octants. So in here, we would be writing to 8 of these. So each individual octant, right? And if you look at sort of how this code is structured, what you can see is it goes per sample direction. And so in here where we do like this push array, what I could probably just do is something like this, right? Where we just say, okay, like the dest index, I guess, is, well, it's going to be per. So I guess I don't even really want to do that, right? What we want to do is for each sample index. No, that's correct. So for each one of these, I just want to go through all of the octants. So like, something like this. And then we just want to do the routine for that octant. And as far as I can imagine, the only difference here, actually at all. So like the only change would just be this, right? Like everything else is exactly the same. The only difference is like the starting values. So in one case, it was going to be half the cell dim. Now it's going to be like 2.5 the cell dim or 7.5 the cell dim in each dimension. But that's the only difference, right? And so, this is a fairly clean way to do this, but it's a little obtuse. I might just do the ridiculous version of this where we just said, all right, we actually loop over each kind, like so. Like, here's the different ones of these we want, right? And when we come down here and we do this push array, we're actually going to have like this desc table thing. And I'm just going to say, look, desc table equals desc for whatever the octant index is. And the octant index is just something we get from compute or get octant index or whatever it is, get octant 4. So it's basically all we would do is say the remainder is whatever we computed it to be, right? So whatever one we're on in this iteration, we get that octant out. And that's it. So, that seems fine. And so at that point, if we know what this value is, right? And I can even put that here, which is sort of our sub-index or something. I don't know what we want to call this. It's not the octant index because that's the thing we're actually calling something's precise, but this is basically just our, oh, you know what? We call this the remainder, which seems good. Let's call it that. So if we have the remainder, then we know what the starting location would be for each of these, right? Inside the cell, we would just have the starting location worked out to be 0.25f times cell dim plus half of the cell dim times that remainder, right? So if we just do the remainder times the cell dim, like with the Handmade product here, then off you go. So that's pretty straightforward. And then everything is the same. So that just computes 8 tables instead of 1. And each table starts with an offset in the octant based on the remainder. And everything else would just work. Now, the problem is this code is going to be hellish to debug. And the reason for that is the same reason I always say. I've said it a billion times. I'll say it another billion times. Almost all bugs come from index problems. All the other things that people always say bugs come from are just, I don't know why, because we never have those bugs, and I don't actually know how many people ever have those bugs. Probably if you're just sloppy, you have them or something. But when you have all of these different indexing schemes, which pretty much only happens when you're trying to write fast code, because otherwise you just use one, the mismatch between the indices, and like you computed would use a wrong offset here, this, that, there. That is just the thing that always produces your bugs. And again, because we have two spatially coincident but effectively disparate grids, that mismatch is always, the more coordinate systems you have, the more bugs you have. It's just, maybe it's just me, but in my experience, that's like where all the time spent debugging always comes from, like thinking about mistakes and thinking about where indices is, or forgetting an offset somewhere, forgetting a divide, right, like all that stuff. And so you try to make it as systematic as possible when you go through it, but is always kind of a difficulty expressing these things clearly in code. And a lot of times if you try to put more structure in place, you end up actually obscuring it even more. So like, it's a hard problem because there's not a lot of good ways to attack it in the languages that we have. So anyway, I don't really know that there's that much more to do besides just when we compute the walk table, we now need to return on the part where we just, set up the corners. That may be it. I mean, I don't know, but I'm thinking about it like that might have been the complete. That might have been it. I don't know that there's anything else left to do. So I think mostly now we're just at the point of like now we've got to go through and find out all the things we did wrong. But I think just in terms like conceptually speaking, that's it, right? So now we just have to go take care of all the bugs that got introduced. So let's start. We'll look at well, for starters, here's one bug. Forgot to put that in place. So we'll take them in order. We'll do crash bugs first. Doesn't look like we have any. So now we're gonna have to take a look at just like errors first, I guess, like actual errors. Let's take a look at what the perf is on it, since I have no idea what to expect here. I don't know, like, again, until we get it debugged, we don't even really know what this number would mean. Where is there it is. So again, like, I hope that box count distribution is accurate. I don't know, but we'll see. So this 4.22, that's like better than we've had before, certainly, like significantly better than we've had before. Like 4.5 was where we were at before. So that's a good sign anyway. But again, we don't know anything about that. We don't have any idea, like this is probably just totally wrong. And if we run this in the game, I'm assuming we'll just have garbage. Yeah, so you can see like there's nothing happening, right? So we need to go through now and find out like where all the problems are here with what's going on. And, we may need to postpone that mostly until tomorrow. At this point, I would say that, it may also be a good time to kind of like, start to pull some of the stuff out from the lighting code that we know we're not going to use anymore. Like the grid raycaster is obviously much faster than the AAB caster now. And I'm pretty confident we can continue to improve the speed, so I don't know that we still need that in there. So, pulling out the AAB tester and streamlining things more might be a good thing to do. I guess, did we already do some of that, though? I don't actually know. I don't remember, like, what stuff we've actually done. I think we did that, right? Yeah. So we've already done that. So I don't even know, like, why is this define still here? Yeah, not sure what the point of that was. So anyway, like, hopefully we can start to streamline this some more too, and just simplify it down from where it is, because it's still quite complicated. And there's probably more stuff we could do here to make it a little bit simpler. But in terms of like, yeah, in terms of what actual test code is in here. So we can also pull out some of these other things. We've got this, and we can go look at the code for compute table fast later as well. We've got it saved in the previous versions of the code, so I don't really need that anymore. We can also get rid of some of the things like the test sphere and stuff. Like, we're not using any of that stuff anymore. And we would have to rewrite it probably if we were going to do any kind of real testing with it. So that stuff I think can also be kind of pulled out of there, which I don't know if we did that already either. But like there's, let's see, internal lending core, build diffuse light maps. The irradiance pack and binaural to normal, those we don't use right now, but I think we will. So I'll probably leave those in there just because we'll probably have to use them eventually. So you can see test sphere in here. We don't really want that anymore either. Looks like this is some kind of a drawing code we left in here just to show where we were in the voxel, which we don't really need at the moment. So that's all fine. Test sphere can go. And that all seems fine. So again, yeah, like just slowly trying to bring this code, which is probably the most complicated code we have in the entire game, right? Just trying to like bring it as much in line as possible, and we'll try to do one more pass over it after we're done. But anyway, we now want to know, like, okay, so what is going on here? Why are we getting no output? Like, what's actually happening? So maybe I guess we'll just step through in HH Lightprof, and we'll see what the actual difference is. So in HH Lightprof, if I turn off optimizations and I step into Grid Raycast, I should be able to take a look at some of these things. So my first question is, how do these things look? Do they make sense? What's going on? So let's take a look at some of these. So here's, just some of the entries into the walk table. Let's just see what they look like. I mean, they seem pretty placid. Those are just grid steps, right? Basic grid steps. Exactly what you would expect. I mean, there's nothing weird. That's pretty straightforward, right? So let's take a look too at some of the other computations here. So like, if you take a look at the initial grid index and the octant index, right? As I run through here, we should get like different octants. And to be completely honest, I guess that's not exactly the pattern that I would have expected. So I guess I can see why, though. So the reason for that is because since we're going in sheets, you would only get alternating, right? Because if you look at how fullcast works, I should say compute lighting. So you can see it steps in ZX. So you'd expect to see 0, 1, 0, 1, 0, 1, 0, 1, 0, right? And then you would expect to see like 4, 5, 4, 5, 4, 5, 4, 5, right? And that is what we get. So that does seem correct. So no real complaints there. Let me take a look at the spatial grid in general. Oops. And I'm just curious about some of these values. That seems fair, kind of what we would expect. Again, really just don't see anything weird here. This all seems pretty placid, right? So to be completely honest, I'm not sure where the trouble's coming in. I would have liked, for my ease of not having to do much work, I would have preferred to have seen something more blatantly wrong, right? But this looks subtle. I don't see anything obviously weird, right? So we're going to look up into the walk table. Here you can see that happening. And we're just going to take a look at you know, what we end up with here in terms of, oh, all this needs to go away, by the way. Like, so the ray dim index, that stuff, sorry, we gotta pull some of this stuff out. I don't want to be stepping through this code. Also, we don't need like a bunch of these values, right? So in terms of the stuff that's in here, we don't need the T values anymore. Those don't have to be here because we're not doing that. So just get them out of the way so you're not cluttering things up. Similarly, none of this stuff has to be here. That's all gone. And I also think these don't have to be here. Like inv-ray depacked. So a bunch of that stuff just isn't relevant anymore. I don't know if sine ray D needs to be here. It does. All right. So just pulling some of that stuff out so I don't have to deal with it. Oops. And off we go. So let's see. I need to step in. That just ran. It ran away from me. So we are doing tests. A lot of those tests have nothing in them, but that's what we would expect because it's a very sparse system. That's just kind of the way it is. So I guess one thing I'm not 100% sure about is I guess we don't really know that it's broken. So, all right. So let's take a look at what happens if I weld it back in. So if you look at how this stuff's working here, again, like this is kind of ugly and I don't really love it. So when we do our Vox cell dim here, again, what I want to do is when we create this spatial grid and we have the spatial cell count, the atlas cell count, and all this garbage, so we need this stuff to be computed differently. So I would want to do this for starters, right? And then when we do the Vox cell dim, I would want to do this, right? So there's basically like a multiplier ratio there on each of those. And that part's pretty straightforward, but the rest of this, so down here, I think this just wants to do a subtraction for the spatial min corner. I think it just wants to do whatever the atlas spatial, whatever the spatial grid's cell dim is. It just wants to be one cell because it's always one cell all the way around, right? So I think that is the way that wants to be phrased because it always has a one cell apron. So I think that always wants to be adjusted that way. And then when we actually do the flat index from part of things over in fullcast, that part's a little squinky. But when we do this, and we do this atlas to spatial grid index offset, that's still going to be 1 all the way around, right? So I think that's the only patching we would need to do to run it in the game. think. Don't quote me on that. And so I'm not really 100% certain. Oh, so, okay, so it turns out it maybe just works. So when we actually did the patching to line the grid up properly in the game, it just worked. So maybe there wasn't anything wrong with it, and I just thought there was going to be. So that's fine. And I think, again, like, we don't really know exactly if we still got bugs because we're kind of just playing it fast and loose as we march down the optimization curve. We're going to have to sort of go through and do that sort of final pass on things. But taking a look at it, in terms of our current speed, again, constant forward march of progress, we've gotten, again, down a little bit lower. Now, one of the problems here is, again, I'm not really sure how far we're approaching. So this is with the larger grid size, right? I'm not sure. I'm still even not sure if that's, I mean, for all we know, we want to be even bigger than that, right? And so, you know, you could imagine going up one more to 9. You could imagine going up to 16. Well, it's not 16, is it? 64, right? So you could imagine continuing to make it more and more ridiculous. But at least now we can see that, like, okay, we have very few splits now, which is good. And we just have a lot more that are, you know, going to actually utilize that loop. And that's a positive thing too. So that's just looking better, right? That's looking significantly better. So what I'd like to do now is really quickly just take a look at what happens, again, if we run the testing without doing the sort of post code. I'm also going to take a snapshot of this. So in the lighting code here where we've got our little timings here, so that's down more around, let's call it 4.3-ish. I mean, these are not precise numbers, so I don't know why I've been pasting them in there, but oh well. So the 2x spatial grid size got us down further again. But what I would like to know is what happens if, you know, we don't do any raycasting, right? How long does this take? So in the lighting code, again, if I just say, look, suppose we don't bother with any of the stuff that you were going to do afterward, which I guess is... So right here, like, let's just suppose we just don't do this code, right? So if you didn't have to do any of the casting at all, so that's 1.02, right? So we now know that we have a headroom, and that's better, which I guess I'm not really sure why, but... right, because that's a little bit different than what we took before. That could easily be within variance, right? That's not particularly variant, so I don't know. We might have improved some things. Who knows, right? Maybe this... Oh, you know what? It's probably the spatial build getting faster, right? So it's getting better. And if we look at the difference between those two, we've only got 3.2 seconds worth of delta between doing nothing. So the grid raycast now is quite a bit faster than it was when we started, certainly. If you took a look at the difference between these two things, we were at 7.2. So where's our... there we go. So we were at 7.2 seconds or 7.3 seconds, right? And we know that 1.2 of those seconds is just the preamble stuff. So if we're talking about 6.1 seconds, and now we've got ourselves down to 4.2. So we've doubled the speed of the raycaster, roughly speaking. And that seems good. I don't know how long the spatial partition build takes, so I might say like build this. So if we just don't do this, right? So I guess the problem there is someone still accesses it. I'm not sure why. Because we're not querying it. Oh, well, you know who is. It's this saucy salamander. Right here. Right. Because that does actually access it to do the testing for whether or not you start it out inside the grid. Oh well. I was hoping I could just kind of nerf that computation entirely. Well, that's okay, I suppose. Actually, let me just back it out like this. If I want to if I want to get rid of the cost of building the spatial partition, what I could do is just say when we do these, just don't do any computations in here. So all of this code can go away. Maybe that would work. So that way I can still test it without, but it still creates something there so people won't crash. I don't know. They probably will still crash. So that's not accounting for anything. Maybe we're not even timing it. No, we must be, because it's in the internal lighting core. So I don't know how that takes 0 time, but apparently it does. Unless I did that test wrong. So in theory, that's just a non-issue, which is what I would expect because it was only done once, right? So it's it really shouldn't contribute much. So that's fine. All right, so let's go ahead and stop there, and tomorrow we'll take a look at some other things. I'll do a quick Q&A. Ooh, that's a tough question from Insobot. Insobot is a rather aggressive questioner. You might say. You might say. Can I run through how the lighting looks now? Sure. It's pretty straightforward, actually, how it's actually working at the moment. And we haven't gone into sampling yet, so we're going to do some different sampling things in here to improve the quality of things. But at the moment, the process is pretty straightforward now. What we do is we have a lighting voxel that is imposed over the scene, and we step through that casting rays out from the center to see what we hit, and we do a gather based on the voxel itself. So whatever the previous frame's voxel is, we gather from there. In order to speed up the ray casting, we have a second spatial grid, which is half the resolution of the voxel, just because the voxel's too granular. And we step through that spatial grid looking for what occluders exist in it, and we do the raycast against those to see what we hit. And that's really it. So it's pretty straightforward. The problem, as with anything, is when you have to go really fast, the code is very dense, because you can't just write things the first way. You have to do them pretty elaborate, right? Like this. So you get stuff that looks like that, which is kind of nonsense, right? But it's just, it's not actually complicated code. It's in terms of what's doing. It's just we had to write it in really obtuse ways because that's the only way to actually, mostly it's because Intel chips suck. It might be a right way to say it, right? If Intel chips had a halfway sane instruction set, all this stuff would look pretty much exactly the same as it looked before we started optimizing it, right? But SSE is like one of the worst vector instruction sets ever designed. So, you get crap that looks like this. Yeah, we'll probably do some denoising in a sense, but we probably won't quite do exactly denoising per se. We will be doing some things to make the lighting more consistent. And then also we're going to spread it out more, but we're probably not going to do literal denoising necessarily, but who knows. Is neon any better? Yes, it's way, way better. Way better. AVX 512 is also way better, but nobody ships anything with it in there, so it doesn't matter. Basically the only chips with AVX 512 support that you can actually use are server machines. So for game programming, it's useless. So AVX2 probably wouldn't help particularly much for what we're doing. But so it's hard to say. AVX2 is tough. On a lot of parts, it's slow. So you probably don't want to use it, and you don't want to mix AVX2 code because it has weird startup penalties and stuff. On Zen, it would probably be a big win, would be my guess. So if we were on a Ryzen core, I bet we'd see some good wins on that. But what I would say in general is it's still just maybe a little too aggressive at this point. So, if you go ahead and take a look at that's just rough. A quarter of the machines on Steam can't run your code. That's just not... I just don't know if that's viable, right? What I'd say about... Skylake X also supports AVX. Yeah, again, Skylake X, just nobody has that, right? Those are server chips. People with game machines don't have that. Here, look. Nobody has it. Literally nobody. So nobody has Skylake. I don't have Skylake X. I don't have a single machine in this office that's Skylake X. It's not a thing, right? It's for server SKUs only at this point, and it doesn't even exist on AMD. There are no AVX 512 parts on AMD. How is Skylake X not server? Isn't it definitely server? I've only ever seen it in server SKUs. Does anyone do desktop builds with Skylake X? Maybe somebody does. I guess it depends on how you define server. Is that... I guess that is not server, maybe. I could see those. I mean, that's a server. I don't who. Maybe like real enthusiast gamers or something would put that in a. I mean, I don't know. Yeah, I mean, I guess I guess one of the things is in my mind. I think I probably don't have a realistic picture of what enthusiast gamers might actually spend on their machine. I mean, I guess there are people out there who spend $1,000 on a gaming CPU. But couldn't we do 2 pass, one with and without AVX2? Not really. So the reason that doesn't work particularly well is that if a CPU has AVX2, it's probably faster than a chip that doesn't have AVX2, so it's unclear who you're optimizing for at that point. Because, I mean, I guess you could just say, well, you turn on a higher quality setting, but typically the people we're optimizing for are for the chips that don't have it, right? You're trying to get things fast, as fast as possible for the machines that wouldn't have AVX2. So this is usually the reason why that kind of a dev process doesn't make any sense, because you're just making the code even faster on machines that already would have run it faster than the actual minimum spec you were trying to optimize for, you know? So those kind of paths only make sense if you're trying to have an additional quality setting. Why is AVX 512 so uncommon? Probably number of registers. Probably. You'd have to ask Intel. End-to-end AMD. Number of registers and size of register would be my guess. I don't know, but that'd be my guess. AVX 512 is a real bear. It's 32 registers, which is way too many registers. I don't know why it has that many. And it also adds mask registers. So it's a disaster. I want to say they do some crazy crap like that. I want to say like the mask registers are aliased with the x87 part or something on modern implementations. Like, I'm not making that up. I think that's actually true. Yeah, so Ice Lake will have AVX 512, I think. So if they ever actually ship any of those in quantity, it would. So, all right, I'm going to wrap it up. All right, thank you everybody for joining me for the episode of Handmade Hero. It's my pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org, and it comes with a source code so that you can play around with it. We'll be taking a look at some other optimization options tomorrow as we continue just trying to make sure the Lightning Code core stuff operates as quickly and as cleanly as it can. That's it for today. Hope to see you back here tomorrow. Till then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.